Hello everyone. Welcome to our channel Chemistry Academy for IIT JEE and NEET. हम टॉटोमेरिज्म सीरीज का आज पार्ट 5 डिस्कस करने जा रहे हैं। हमने बेसिक टॉटोमेरिज्म डेफिनेशन, डिफरेंस विथ रेजोनेंस, मैकेनिज्म, डिफरेंट टाइप ऑफ कार्बोनिल्स में इनॉल कंटेंट सब कुछ डिस्कस कर लिया है। आज हम करने जा रहे हैं व्हाट विल बी द इफेक्ट ऑफ कीटो इनॉल टॉटोमेरिज्म ऑन द प्रॉपर्टीज ऑफ कार्बोनिल कंपाउंड्स। तो आइए स्टार्ट करते हैं। तो देखें टॉटोमेरिज्म पार्ट 5। तो टॉटोमेरिज्म के टोटल प्रॉपर्टीज ऑफ कार्बोनिल मॉलिक्यूल्स पर बहुत सारे इफेक्ट होते हैं। देयर कुड बी मेनी, बट द मेन इंपॉर्टेंट 5 टाइप्स आर ऑन द स्क्रीन। फर्स्ट, there could be loss of optical activity of alpha chiral center. अगर मॉलिक्यूल में अल्फा कार्बन एक कायरल सेंटर का रोल प्ले कर रहा है तो उसकी ऑप्टिकल एक्टिविटी थ्रू टॉटोमेरिज्म खत्म हो सकती है, या मैं कहूं उसका रेजमाइजेशन हो सकता है। डिफरेंट टाइप ऑफ आइसोमराइजेशन थ्रू इनॉल फॉर्मेशन। डिफरेंट टाइप मतलब क्या? उसमें स्ट्रक्चरल आइसोमरिज्म का बदलाव आ सकता है, उसमें ज्योमेट्रिकल आइसोमरिज्म का चेंज आ सकता है। तो अलग अलग तरह के स्ट्रक्चरल या कॉन्फ़िगरेशनल आइसोमरिज्म चेंज हो सकते हैं। देयर कुड बी एक्सचेंज ऑफ अल्फा हाइड्रोजन विथ ड्यूटेरियम when they are placed in D2O. Heavy water में अगर हम रखें तो अल्फा हाइड्रोजन्स कैन बी एक्सचेंज विद ड्यूटेरियम from the solvent. Alkylation of alpha carbon of carbonyl molecule. अल्फा कार्बन पर हम H के जगह पर अल्काइल ग्रुप्स का इंट्रोडक्शन कर सकते हैं थ्रू टॉटोमराइजेशन, थ्रू इनॉल और इनोलेट फॉर्मेशन. Halogenation of alpha carbon. We can similarly also introduce halogen at alpha position through enol or enolate formation. इनमें से हम अभी इस पर्टिकुलर वीडियो में इसकी पहली दो प्रॉपर्टीज डिस्कस करने जा रहे हैं, दैट इज लॉस ऑफ ऑप्टिकल एक्टिविटी ऑफ अल्फा कायरल कार्बन एंड डिफरेंट टाइप ऑफ आइसोमराइजेशन थ्रू इनॉल फॉर्मेशन. दे आर एक्सट्रीमली इंपॉर्टेंट विथ रेफरेंस टू डिफरेंट कॉम्पिटिटिव एग्जाम्स एज वेल एज 12th बोर्ड. वॉच केयरफुली. तो हम सबसे पहले देख रहे हैं लॉस ऑफ ऑप्टिकल एक्टिविटी ऑफ अल्फा कायरल कार्बन. अब ये जो अल्फा कायरल कार्बन है, ये इस समय हम यहाँ देख सकते हैं कि दिस कार्बन is sp3 hybridized with 4 different groups on it, and that is how it is acting as a chiral carbon. हमने यहाँ पर इसका पूरा ऑप्टिकली प्योर एनांटियोमेरिक फॉर्म ले रखा है. इसका मतलब है either I have 100% dextrorotatory enantiomer of this molecule, or I have 100% levorotatory enantiomer of this molecule. We cannot have a mixture. You have to have only one out of the two, and it should be totally pure. Now, when this form enol, then this alpha carbon is now converted to sp2 geometry. This alpha carbon is now converted to sp2 geometry, and sp2 geometry, as you all know, is a trigonal planar geometry. It is planar geometry, trigonal planar. So when this enol has resonance, the alpha carbon is becoming anionic in nature, negative. It can now act as a base. मीडियम में वाटर प्रेजेंट है, वाटर से ये बेस सेंटर, ये अनायन सेंटर will accept H plus. As a result, this carbon is again becoming sp3 from sp2. But when it is becoming from sp2 to sp3, from sp2 to sp3 change, there is an equal probability that hydrogen would have attacked on this sp2 from the upper side or from the downside of this trigonal planar. As a result, there is an equal probability of forming both dextro as well as levo rotatory isomers of this molecule. So, in the final mixture, I'll have optically inactive due to formation of racemic mixture. Because of formation of racemic mixture, the final solution of this molecule will behave as optically inactive. Correct? So what we saw, that we had an alpha carbon having one hydrogen and is acting as a chiral center. Then we lost the optical activity when we kept it in a medium where enolization was possible. But it is not always the case. So let us see different possibilities. If assume that if I have a molecule in which the chiral center is not the alpha carbon but next to alpha. Alpha, I can say the beta position is now acting as a chiral center. So let us see what will happen. Yes, enol formation will take place, but enol is formed from the alpha carbon. So there is change of hybridization from sp3 to sp2, again from sp2 to sp3. This equilibrium is there, but in this entire process, this chiral center remain untouched. It has no involvement in enol formation or anion formation. So ultimately, if the molecule is having a chiral center which is not participating in enol formation, then it will continue to have its optical activity. This type of molecules will not lose their optical activity due to enolization. Next, we see that if the alpha carbon is chiral but is not having any hydrogen over there. So now this site where the chiral carbon is present cannot participate in enol formation, and so it will not lose its optical activity. Enolization did take place, but it is on the site which was not chiral. So there is no effect of this enolization on the chiral center, and its optical activity, its configuration remain unchanged. Next example, we are seeing that the chiral center this time is not exactly alpha or beta, but can be at any place which can form an anion such that anion can resonate with the carbonyl carbon. Please check it again that yes, this carbon which is chiral is nowhere directly connected to carbonyl. But when we keep it in an acidic or basic medium, this H will be lost because the anion is resonating and is stabilized by the carbonyl resonance. I have drawn these three resonating structures. See, this can resonate to alpha position anion, and this alpha position can go to resonance with carbonyl oxygen. So these are the three resonating structures of the molecule. As a result, this particular molecule can definitely form anion at the chiral center. Again, when this center accepts the H, it is again becoming from sp2 to sp3. And when it is becoming from sp2 to sp3, there is equal probability of forming either dextro or levo. As a result, the structure will lose its optical activity at this chiral center. But not only this, here where I am marking at this particular time, and you can see on your screens that in this point of resonating structure, I have lost the double bond on the original given molecular site of double bond. So if this was having any particular type of GI as either cis or trans, then it will also have impact on its geometrical isomerism due to this particular enol formation. So optically inactive due to racemic mixture formation, and even its geometrical isomerism will change. So next we move to a different type of isomerization can also be observed. A different type of isomerization through enol formation. We have already seen that enantiomerically pure solutions converted to racemic mixture through enol formation. We can also have a isomerization in which there is change of structural isomers from one to another through enol formation. Right? A very basic example. For example, if I have an alpha hydroxy ketone like this, it formed an enol. You can see that this particular carbonyl has alpha carbon over here. If I exchange alpha hydrogen and carbonyl, I will get this enol. And this enol, I have encircled two. One is the red part, one is the blue part. So if the red part enol undergoes to the keto form, again it will be changed to alpha hydroxy ketone. If the blue part goes to enol say keto, then you will have an aldehyde. Alpha hydroxy aldehyde is formed, and these alpha hydroxy ketone and alpha hydroxy aldehydes are functional isomers of each other. A very wonderful example of this type of functional isomerism change is observed in biomolecules chapter, where D-glucose is changed to D-fructose and also to D-mannose through this type of enol formation. So you can see this glucose is there, IUPAC position number 1, 2, 3, 4, 5, and 6. It is a 6-carbon compound and with 4 chiral centers, 2, 3, 4, and 5 carbon position carbons are acting as optically active. So when this D-glucose is kept in alkaline medium, it is now changed to enol. As a result, the alpha carbon of carbonyl is now becoming sp2 hybridized. I just marked it with yellow star. You can see on your screens is now sp2 hybridized. So it has lost its optical activity. Now again, as I just shown 2 minutes back, that this enol can either undergo to keto formation on upper side of OH or the second number of OH, on the carbon number 1 OH or carbon number 2 OH. If it uses carbon number 1 OH for enolization, then you will observe that the mannose will be formed. But again, when this sp2 is changing to sp3, this carbon can either be having dextro configuration or R configuration, or it can have S configuration. As a result, this enol can either form a D-mannose or D-glucose. If the enol selects this carbon number 2, right? If it selects this carbon number 2 OH, I'm encircling this time with red, for keto formation, then as a result, you will have fructose. Now, in the mixture, you are having D-glucose, you are having D-mannose and D-fructose all present together. You may start from any of these isomers in the medium. You will ultimately have all 3 present together in a fixed amount at a particular temperature and pressure. As a result of this enol, I can say that D-glucose is converted to D-mannose and fructose, and similarly for other molecules too. D-glucose and D-mannose are diastereomers of each other. What are diastereomers? Diastereomers, particularly here I am referring such two optical isomers which are not mirror images of each other, are diastereomers. They can have point of difference at any carbon. It could be 1, 2, or more. So in D-glucose and D-mannose, they have difference in their configuration at C2. If you see, carbon number 2 is having a different configuration. In one, it is resulting in glucose. In other configuration, it is giving D-mannose. D-glucose and D-fructose are functional isomers of each other. So as a result of enolization, we have seen there is a change in the structural as well as the stereoisomerism of the molecules. So at this point, we are closing this part 5 of tautomerism, and we'll have the last and the final video on tautomerism. That will be part 6 for the rest of the 3 properties that we have shown in the initial part of this video. Thanks for watching. If you liked our video, do not forget to subscribe